Welcome back to the tutor, and this is electronics. I'm your tutor, Joey Monday, and as we did in our previous video, which was just a revision to see what we need to bring from electronics 1 to electronics 2. And as I said, if you understand that part, which means you have covered a big part of electronics 2. And on today's video, what we are going to do, we are going to discuss some important part that you need to keep in mind, their concepts, so that you understand that I do this because of this. But before we go forward, what we are going to do is we are going to do and have a look on some application of a transistor. And then one of them is the BJT amplifier. It's just the application of our transistor. Okay, so let's have a look on our application of a transistor. So under our application of a transistor, first of all, we must keep in mind that a transistor always has 3 states, and one of them is that our transistor can operate as a linear. Linear is one of the states. Okay, so what happened with a transistor is that already this is the representation of our transistor. So in order for our transistor to operate as a linear, and a linear is already an amplifier, our base emitter junction is forward bias. So our base emitter, this is the base, and then this is the emitter, must be forward bias, which means you have a positive and then the negative, because it's basically a diode. Okay, so this junction must be forward bias. And then again, in order for it to be linear, the base collector junction must be reverse bias. What happens when we talk about reverse bias? It's all about that this junction must be reverse bias, so which means we know already that we're gonna have a positive there from the collector, so that already this will be reverse bias. Okay, and then in another application, another state, saturation. In the saturation, we need to make sure that our BE junction and the BC junction are forward bias. So which means the 2 junction here must be forward bias. Another state is the cutoff. In order for our transistor to be in the state of cutoff, the BE junction and the base collector junction are reverse bias. So you can see that we have been talking about bias. So by the way you bias your transistor, it can either be in 3 states: linear, saturation, or cutoff. Okay, and then what else can we have in mind now is considering the 2 states, saturation and cutoff. If you consider the 2 states, saturation and cutoff, our transistor can be used as a switch. You didn't do the lab, you will see that. But our transistor is in cutoff when you have a 0 base voltage. Okay, and therefore it considered to be a open switch. So if, for instance, you add a light here, a small LED light here, this small LED light here, because it's in cutoff, it won't switch on. The light will be off. Okay, but if it's in saturation, it's considered to be a closed switch. And then if it's a closed switch, which means there will be a current flowing and our lights will go on. So okay, so the combination of saturation and cutoff, we can use our transistor as a switch. Therefore, we can open it when it's in cutoff, close it when it's in saturation. Okay, and then another things we can have a look, considering the linear state. When our transistor is in linear state, we can use it as an amplifier. What do we mean by an amplifier? Already, that's our BJT amplifier, which is your chapter 6. It's all about the BJT amplifier, the application of your transistor when it's in linear state. So let's have a look. Application and amplifier operation. First of all, we need to bias our transistor in order for our transistor to operate as a linear. As from the previous we have explained, it was all about the way you bias it. And then the voltage divider bias is the one you use. In the previous video, I did the calculation on the voltage divider. So the voltage divider that we did, it was a bias. But the question now, what is a purpose? What is the purpose of biasing? The purpose is to establish a Q point about which in current and the voltage can occur. Can you see? So for instance, if I come, I draw this curve like this. Okay, this is our reference. Okay, so therefore if I come, when I talk about the Q point, as I explained it in the previous video, it was all about VCE and your IC. So those two components, if you calculate them, will give you your key point. Okay, so therefore when you come here, you can see that if you bias it, your Q point may go somewhere there. Let's say your VCE is there after biasing your diode. Okay, so once you bias it, what will happen now? What will happen is that the variation in current and the voltage will occur at your key point. Okay, so the key point, the base reference is not at 0. We move it to VCE so that it's at VCE where our variation in current or voltage will be. So which means this VCE can be changed the way we bias. We can move it to here, we can move it to there, but by the way we bias our diode is just to get our Q point where our current and voltage is going to do the variation. Okay, and therefore let's have a look at a linear amplifier. This linear amplifier provides amplification of a signal without any distortion, so that the output signal is an exact amplifier replica of the input. Okay, so what happened is, first of all, from the video that we discussed, we need to come and bias our diodes, and to bias it, we're gonna do a voltage divider. So can you see? So I will put it in red. So this voltage divider is just to bias our diode so that we're gonna have a Q point. Okay, so after getting your Q point, now you're gonna use it as your an amplifier. What does that mean? You come with a AC signal, a V in. Okay, so this V in will go through this diode, this transistor, and when it go out, we can see that we increase that our V in. Can you see? So the purpose of a linear amplifier is to provide an amplification of a signal without any distortion, so that the output signal is an exact replica of the input signal. Okay, so now we'll be dealing with 2 circuits. Therefore, we're going to talk about it deeply in our next page. Okay, so what will be our next page? It's all about, first of all, let's have a look. What is the purpose of these two, the 3 capacitor? Okay, so with a capacitor, when it's in DC, it's like it behave like a open switch. Okay, so when this DC current, this current is coming across the capacitor, this capacitor will behave like a open switch. There won't be any DC current flowing through it. Okay, so that is the purpose of those 3 capacitor. Can you see? So what happened is that our capacitor 1 and capacitor 3 are called the coupling capacitor. Why? Because from these 2 capacitor, there won't be any DC current flowing. All the DC current, when they come across this capacitor, there won't be any current flowing for DC current. Even here, when it comes, there won't be any current, DC current flowing across those capacitors. So can you see? Okay, but now look what happened. If you come now with a AC current, that AC current, which is our signal, this current will flow through those capacitor, because those capacitor behave like a closed switch when there is a AC current. Can you see? And then here it's gonna be happen the same. Can you see? So the purpose of this capacitor in our circuit is to make sure that when we're gonna combine a AC source and a DC source, the 2 current doesn't match each other. Can you see? Because what we need we want to amplify is a AC signal, because with AC we know that we're gonna have a sine wave. Can you see? So Therefore, this capacitor will allow only a AC current to flow through it. But when a DC current is coming, it won't flow because it behaves like a open switch. So the things to note now is that with a capacitor, in DC current, this capacitor is considered to be a open switch. But with AC, this circuit is considered to be a closed switch. So therefore, when a DC current is coming across the capacitor, it won't flow because it's open, but across the AC signal, which is our signal, it's gonna flow. Can you see the magic? So we combine a DC analysis and DC volt current and a AC current, but because of those capacitor, the DC current won't flow, but the AC current will flow through it. And then what happens when the AC current is flowing? When it come across a AC source, a DC source, this will behave like a ground. It's gonna be open. When the AC current is coming, there won't be any current flowing back into our DC source. Okay, so first of all, we say S1 and S3, those two capacitor, they are coupling capacitor. Okay, and then what will happen to our C2? C2 is a bypass capacitor. Why bypass? Can you see? Because when you come with your AC current, this current will flow here, and then this current, once it arrives here, you can see that this is a closed switch. The current will take the easy path, the current will flow over this, and we are doing what? We are bypassing R1, and then when it's coming here, this current will go. This is a ground when the AC current is coming. Okay, and therefore our RC as well is connected to the ground, and then this is connected to the ground. Okay, so this is AC analysis. But if we have to do DC analysis, what will happen if a DC current is coming? This current, it cannot flow there because it's open. This current can only flow here. When it goes there, it cannot flow because it's open. This current will go like this, and then this current will go down, and then will come like this. This current cannot flow there because it's open. Can you see? So we are doing DC is to bias, AC is to flow our signal into our capacitor. Okay, and therefore their purpose is to block the DC current, the purpose of those capacitor, and then to prevent the internal source resistance and the load resistance from changing the bias voltage. Okay, and then the transistor AC model, what we need to keep in mind is that when our capacitor, there is a AC current flowing into this capacitor, AC current flowing through this capacitor, what will happen is that there will be a creation of an internal resistor, and this internal resistor is only in our AC circuit, and then to calculate that internal resistor is going to be RE. Can you see? So here there will be a internal resistor, R emitter, that will be created in our AC circuit, and then to calculate it, we're gonna use this formula. Can you see? So therefore, the first thing we need to calculate our emitter current in the DC circuit, in our voltage bias. Okay, in our voltage bias. So you come here, like in our previous video, you're gonna do those calculations for DC circuit just to get your E emitter, your current emitter. Once you know your current emitter, that current emitter will come to help you to calculate the resistance of the AC circuit. Then you can do calculation for AC. So that's what you need to know, to keep in mind. And therefore, we say we're gonna have our R in base. Because of that, remember, with a DC, you were calculating R in base, and this also is applicable. After calculating your E emitter from DC circuit, now you're gonna calculate your R in base. You have your R emitter, then calculate your R in base. Okay, so those are the 3 points that you need to keep in mind from a transistor as a AC model. Okay, and then DC analysis, as I said, DC analysis, remember, is we are combining DC and AC. In a DC circuit, what we're gonna have in our circuit, it's gonna be only this. We're gonna consider only this part. Can you see? When you're doing a DC analysis of an amplifier. And therefore, to do our calculation, we say it's gonna be all this calculation here, but we're gonna stop to E emitter, because E emitter, the current emitter, will help us to calculate the internal resistance for the AC circuit, so that we can calculate the R in base for the AC circuit. That's what you need. You come here, you look for your E emitter. Okay, your E emitter for the DC circuit will help you to calculate your internal emitter current, a resistor for your transistor. Okay, then you can carry on with AC calculation. Okay, and therefore, as we said, with the circuit, the first thing we have to do is to check if our circuit is stiff or if it's not stiff. We're gonna check if this circuit is stiff or this circuit is not stiff. Okay, and then I've explained it in the previous video how to check that. Okay, and therefore we move our AC analysis. If we do our AC analysis, as I said, with the circuit, with AC analysis, you're gonna see that the current will flow like this. So we have a parallel of what? R1 and R2, because this is already a ground. The DC become a ground in AC. So you see, you come R1 and R2 are in parallel. Okay, and then you can see that they are also in parallel with what? With this branch, and then they are also in parallel with that branch. But because here we're gonna have a R emitter, that's an internal resistor, which we're gonna calculate 25 millivolts over E emitter. E emitter, where do we get E emitter in DC circuit? Okay, and then after here, what you're gonna see is that after here, you see that our RC, can you see? You have your RC connected to the ground as well. Okay, so if in this circuit without a input signal, but with an input signal, you're gonna see that now you have a R series, okay, series, and then this other that in parallel. Okay, so let's have a look on what will happen under the calculation. So as I said, because of this parallel we have here, we have to calculate the R in total. Can you see? You have this and that. This will give us a R in total. R in total is basically a parallel of what? R1, R2, and R in base. R in base, how do we calculate our R in base? R in base, we're going to give a what? Beta AC, because we also have a beta BC. AC times what? R E emitter. How do we calculate our RE emitter? We take 25 millivolts divide by what? E emitter. How do we get our E emitter? E emitter, we're gonna get it from our DC circuit, from our DC calculation. Okay, and therefore you can calculate now your V base. How do we calculate your V base? Your V base, you can see that it's gonna be the voltage across the voltage across this. Okay, so you apply a voltage divider. You say R in base divided by what? You can see we have a series of what? R series plus R in base. Then you apply your voltage divider formula. R in base divided by RS plus R in base times our V source. Okay, and then we move. Our output resistance is almost close to our RC. And then the three configuration of an amplifier. First of all, we have the common emitter, we have the common base, we have the common collector. But as we're gonna do today, just the common emitter. And then what we mean by a common emitter? We mean the emitter as the common ground to the AC signal. Can you see? So our AC signal is this. The ground to this is going to be the same as the one for the emitter. The ground to these two, they have a common base. Okay, So that's what happened there. And then when you see our CE amplifier, CE, what is that? CE mean common emitter. CE mean common emitter, sorry. Okay, and then therefore we're gonna do our calculation. As I said, after doing our DC calculation from the previous video, you can watch how to do this calculation. In the DC calculation, what we are looking for is just to calculate your E emitter. Okay, once you know your E emitter, you come now, you calculate your R emitter for the DC, internal emitter resistance. Once you get it, now you calculate your R in base total, and then now calculate your R in base. How to calculate your R in base is gonna be beta AC divided by that. Then you substitute the value there. Okay, your R out is close to that. Okay, this other part I will explain it where we are going. So basically, those are the small calculations that you have to do, but you need to understand them as well. Why are we doing this? Okay, and then once we move, we're gonna talk about the voltage gain. By definition, is the ratio of the AC output voltage at the collector VC to the input voltage at the base. That's how you calculate your voltage gain. The attenuation, the reduction in signal voltage as it passes through AC circuit and correspond to the gain, to the gain or less than 1. That is our attenuation. You have the overall voltage gain, which is going to be the attenuation times our voltage gain. You have the current gain. These are just some formula that you need to keep. And then you have our power gain. That's how you calculate your power gain. And then now we're going to talk about the effects of the voltage gain. When it comes to the effects of our voltage gain, what we need to keep in mind is that we need to make sure that the R emitter that we put, okay, the R emitter that we keep, or the R emitter that we put, must be always equal to 10 times XC, which XC, the capacitor that we're gonna put there. Can you see? So we need to make sure that this must be equal to that to avoid the effect of the bypass capacitor. Okay, so if we have this, we can see that our voltage gain with the bypass capacitor. Okay, so you can see that when you have a bypass here, when you have a bypass, the voltage gain, how do you calculate it? You're going to calculate it like this, because you can see that here the current will flow 3. It's already bypassed. This is not part of the circuit. Okay, so if there is no any bypass, now your voltage gain is going to be calculated by this. You have to consider this resistance emitter here. Okay, and then our next video, we're going to have a look on the effect of the loads. Now we're going to have a look on the effects of the voltage gain, effects of the load on the voltage gain. So as you can see, a load is this R load. Okay, so because if we connect our loads here, you're gonna see that our RC and this R loads will be in parallel, so therefore we have to calculate a RC parallel. Okay, it may happen sometimes they don't give you a load. If it's not given, you just calculate, you consider RC. But when it's given, now you must consider that load as well in part of our circuit, because the two will be in parallel. So that's what's happened. You calculate those parallel, and then our voltage gain will be like this. And therefore, we're gonna have a look on our stability of the voltage gain. Is the measurement of how well an amplifier maintains its design value over the change in temperature for the transistor. And then to do that, we need to swapping RE to stabilize the voltage gain. How do we do that? So we can see that's basically what happened. Okay, so in order for us to stabilize our voltage gain, we're supposed to put just one emitter resistor like that, okay? But now we come here, we split the emitter into two, so we bypass only one part of it. Can you see that? So when you come here, if they give you such question and then you have to analyze, let's do our DC analyze. Our DC analyze, we come here from the source, this from the source, this circuit here will represent our DC circuit. This will be our DC circuit. So when doing the calculation to look for your E emitter, this will be your DC circuit. But now if you have to do your calculation for AC circuit, now look what happened. You're gonna have this R1, okay, it's in series with what? A parallel of what? R1 and R2, and as well as R in base here, okay? But look here now what happened. Because of the bypass, we only gonna consider R1, but RE2 is bypass, okay? And then now on the output, we only gonna have our RC, which is in parallel with R3. So we have this parallel, and then we have already explained you how to calculate this R in total and our RC when we have a load. Okay, so that's basically everything that you have to know, but I will try to walk through an example so that you can understand exactly how to approach all this problem.